Assalamu alaikum. Let's start our lecture on detection, where we're discussing probabilities, prior probability, and posterior probability. After that, we have how to choose the threshold. So it's maximum likelihood ratio test and maximum a posterior criterion. So we have two hypotheses, H1 and H2. If the probability of having S1 in the test static signal, that is Z, Z is a test sample, you can say test sample Z. If the probability of receiving S1 in Z is greater than probability of having S2 in Z, then we will choose hypothesis 1. If probability of S2 in Z is greater than probability of S1 in Z, then we will choose the hypothesis H2. Now the problem is that a posterior probabilities are not known. Then so we use the Bayes theorem. Bayes theorem for a particular probability Si, I can be 1 and 2, and the test signal Z is equal to probability of having Z as Si and prior probability of Si, that is P of Si, and the probability of Z. So 3.61 is your typical Bayes theorem. Now, if we replace the two probabilities with this Bayes theorem expression, then that will be look like this one. The probability of S1 is here and the probability of S2. These probabilities that we are determining through Bayes theorem. So this is probability of S1 having S1 in Z and probability of having S2 in Z, and the two hypotheses are given H1 and H2. So if probability of having S1 in Z is greater than the probability of S2 in Z, then we choose hypothesis 1. As you can see, if it is less than, then we will choose hypothesis 2. In both these sides, P of Z is same. So we cancel out, P of Z will be cancelled out on both sides. The remaining will be these expressions, posterior probability and the prior probability, both are here in the remaining equation. So this called maximum of posterior criterion. If you rearrange the two, you will get this one. This is called likelihood ratio test. That is 3.62. However, the probability of S2 and probability of S1 are same because we have only two signal levels, 1 and 0. So the probability of having S2 and S1 is 0.5. Before actually receiving the actual probability, the prior probability that we know of these two signals is 0.5. As we take an example from head and tail, before even tossing the head and tail, for different events, we know that the probability of occurrence of tail is 0.5 as well as head, it is 0.5 because there are only two outcomes. So the probability of getting one outcome is 1 by 2, so 0.5. Similarly here, PS2 is equal to PS of P of S1 is equal to 0.5. So we can replace this P of S2 and P of S1 by 1. So that is your maximum likelihood ratio test. So if it is likelihood ratio test, then there will be probability of S2 and S1 hold. If it is maximum, then it will be 1. So this is known as the maximum likelihood ratio test because we are selecting the hypothesis that corresponds to the signal with the maximum likelihood. So the maximum probability of having P of S2 and P of S1 is 0.5. So in terms of base criterion, it implies that the cost of both types of error is the same. So the error will also be 0.5. So if you choose PF of S2 instead of PF of S1, the chances of choosing the incorrect will be the same. So the cost of both types of error is also same. So we can write this P of ZS1 and P of ZS2 in terms of the Gaussian distribution function, as you can see on your screen. This is called maximum likelihood binary decision, where you can see we have the likelihood of S2, same as the likelihood of S1, and we have different levels lying on different levels against the P of Z and P of Z S2 and P of Z S1. And that is in static signal, that is Z of T. That is we have A1 and A2. And this is gamma naught is your threshold. And one signal is received at Z of AT and one is at Z of AT. So Z of AT on level 2. So its amplitude is lower than the uh, on level 1, that is on the P of ZS1. So this particular Z of AT may belong to P of ZS of 1 because its likelihood of having S1 is greater than the likelihood of having S2. Whereas gamma naught is exactly in between. On one side it is A2 half, on other side of hypothesis is A1. And we can replace N with Z minus A1 and A2. So probability distribution function H1 and H2, that is hypothesis H1 for S1 and hypothesis H2 for S2 is equal. We did nothing, but we just replace N with Z minus A1 and Z minus A2. As you know that the received signal will be the combination of actual signal plus the noise. So you can calculate the noise when Z is equal to AI plus N. So N will be equal to Z minus AI. So instead of AI, we will have A1 and A2. So instead of having these probability distribution functions, we can replace their values in terms of this AWGN distribution, and the equation will becomes 3.63. So let's solve this one. When you solve this one, you can see this this expression is same. So we cancel out even 1/2 is same. This one is also same. This one is also same. We have Z A1 minus A2 square minus A1 A2 square 2. So when you solve this one, 3.63, you will have this 3.64. Then take the log on both sides. We will have ZA minus, so this exponential will be cancelled out in the log. So now the values will be free. On other side, we are also taking the log L of Z, log L of Z is equal. So these will be free from the exponential value. So exponential will be cancelled on the log. And 3.66 comes from 3.65. When you solve this one, you can take this side on the other side of 0. So that will become positive. On one side, we will have ZA minus A2 divided by the psi square. On other side, we will have A1 minus A2 square divided by 2 psi square. So that is this factor. So that can be written as A1 plus A2, A1 minus A2, that is A square minus B square is equal A plus B and A minus B separately in brackets. So we can cancel out this term A1 minus A2 here. and A1 minus A2 because both are on in the numerator on both sides. So that will be cancelled out in the next step. So then we will have 3.67. That will be like this one you can see. So this one we cancel out as I already told you. So the Z will be A1 plus A2 divided by 2. That is equal to gamma naught. So that is your test static. So where is Z, where Z is the minimum error criterion and lambda naught is the optimum threshold. So for antipodal signals, when S1T is equal to minus S2T, that is A1 minus A2, then this test static will be greater than 0 and less than 0. If it is Z is greater than 0, then we will choose hypothesis H1. That means S1. And if it is less than 0, then we will choose S2. That is hypothesis S2. So as we have already represented these hypotheses with different S1 and S2. So that is your lambda naught is your minimum error criterion. Z is the minimum error criterion. This is the way if you used to choose Z in accordance to this, then there will be minimum error criterion. So using this test static and the hypothesis, the errors can be minimized. Means we cannot make an error of choosing S1 instead of S2. So in this way, we can minimize the error and optimize the threshold. And optimized threshold, we say gamma naught, and that is equal to A1 plus A2. And if two signals are antipodal means they are opposite to each other, means they are like one is at means 180 degrees. Antipodal means they have the opposite direction. That is S1T is equal minus though they have the same magnitude but the different direction. Then A1 is equal to minus A2. In that case, that lambda naught will be equal to 0. That is only when the two signals are the antipodal signals. So this is the repetition of the same slide, previous slide. So moving forward. Now let's see how to calculate probability of error. So error will occur when S1 is sent and S2 is received. Or we make a wrong decision that S1 was transmitted, but our hypothesis or the test static become S2 means we chose the wrong hypothesis and the threshold was incorrect. So we did this error. So the probability of choosing H2, okay, while supposed to choose S1 and S1 shows the hypothesis H1. So the no error means we choose H1 when S1 is transmitted. So that is not an error. But if you choose H2 and S1 was transmitted, then that is error. So P of choosing hypothesis H2 while S1 was transmitted, that is equal to probability of error and S1 means testing S1 and we choose hypothesis H2. That means we make an error. So that probability is represented as PE, probability of E provided S1. So that is equal to minus infinity to gamma naught and P of Z S of 1 D of Z. So that is your this one minus infinity to gamma naught. So that is your gamma naught. And that is your S1. Where S2 is sent and S1 is received. So that was the opposite. And that is from gamma naught to infinity. And that is P of Z S2, this one. And then the total probability of error is the sum of the errors. So we can say that total probability P of B is equal to sum of the two probability, that is I is equal to 2 and PE comma SI, and that will be equal to PE S1 P of S1 plus PE S2 P of S2. Base theorem, but S1 will be same. So that will be not here. That may be cancelled out. P of H2 S1, P of S1 plus P of H1 S2 and P of S2. That is the total probability. But we know that the probability of S1 and probability of S2 is 1 over 2. So we can take common 1 over 2 and the two probabilities are here. 1 over 2 probability of having H2 while S1 was transmitted and probability of having H1 while S2 was transmitted. By similarity, both will be same. Both will be equal to each other. So that we can only say we can by similarity we can choose only one, that is P of H1 S2 or P of H2 by S1. अगर ये same है similarity है तो these will be added, so that will be twice of these probability of error. पिछले because we already said that in the previous slide, the cost of two errors will be same. The cost of both types of error is the same. Means the probability of means value of this probability, that is one probability. This value of this probability is same as this one. So that will be, when you add these will be 2, 2. And we already have 2 here. So 2, 2 will be cancelled. And the remaining will be either P of H S2 or P of H2 S1. So numerically, probability of bit error is the area under the tail of either of the conditional distributions of P of Z S1 or P of Z S2 and is given by. So this is again a PDF probability distribution function. So AWGN, using AWGN distribution, we can replace this P of H1 S2 by Z minus A2. And the remaining equation is same, that says from gamma naught to infinity. Because we choose to have the other side. This one, that says from gamma naught to infinity when we have this one, probability of H1 and S2. So same is here, probability of H1 and S2. So in that we will have this equation. In that case, probability of total probability will be equal to this expression. So what we did here, we replaced this Z minus A2 by psi naught by U. And the whole equation will be now can be written as like this one, where gamma naught will be modified. Gamma naught then will be now A1 minus A2 by 2 psi naught 1 over 2 pi exponential minus U square by A2 by 2 and du. The above equation cannot be evaluated in closed form, so hence we use the Q function. So when Z is greater than or equal to 3, we use this equation. Otherwise, when Z is not greater than or equal to 3, we will use the Q factor Q function table that is given in the appendix of the Barnard Explorer book. Even you can find on the internet, and that put for A1 minus A2 by 2 psi naught, that is the limit of U. So this is table for computing Q functions. If Z is 1.0, then Q of Z is 0.5 and Z is 0.0. Similarly, you can have the values up to 2.9. Because when Z is 3 and greater than 3, you can have this expression that you can solve. Then we have generalized one-dimensional signals, one-dimensional signal constellation S1 and S0. That is M is equal to 2, one is plus A, one is minus A. So the two signals are opposite in direction. So that is, so then when we say S1 plus S0, that will be equal to 0 because two are plus A and minus A. So these are the antipodal signals. M is equal to 4. Again, we have antipodal signals, but we have two on each side. Binary antipodal signals, binary orthogonal signals. Then we have the constellation diagram. Constellation diagram are useful when we determine our digital modulation high order schemes. So in a method of representing the symbol states of modulated bandpass signals in terms of their amplitude and phase. So when we represent symbols with their amplitude and phase, we call them a constellation diagram. In other words, it is a geometric representation of signals, and there are three types of binary signals. Antipodal signals, they are same in value, but they are opposite to each other due to their direction. So they will be like S1 T to is equal to minus S0 of T. If you add them, you will have the 0. One are on off or one dimensional signals, either on or off with signaling points falling on the real line, like ASK on off keying. We also know that. So we represent one signal which on state and we represent another signal with the off state. So one should always be 0. Another one should always be high. So in terms of plus A minus A, one will be 0, other one will be plus A or minus A. So like this one, these are the uh, on off signals where S0 is equal to 0 and S1 is equal to square root E. Others are the orthogonal that requires a two-dimensional geometric representation, since these are two linearly independent functions, S1T and S0 of T. So this one is having same values, square root E, amplitude is square root E, but they are orthogonal to each other. Means one is at 0 degrees and another is 90 degrees. Typically, the horizontal axis is taken with as a reference for symbols that are in phase with the carrier cos omega ct, and the vertical axis represents the quadrature carrier component, that is sine omega ct. As we know that cos omega ct, that is cos 0 is equal to 1, and sine omega ct, that is sine 90 is equal to 1. So we represent in phase, that is on the horizontal axis with the cos function, with the cos angle, and the one that is on the 90 degrees, that is the quadrature component or the y-axis component or the vertical axis component, that is represented with the sine omega ct, because sine 0 is equal to, or sine 90 is equal to 1. So error probability of binary signals. So we know that P of B is equal to function of A1 minus A2, A naught divided by 2 sigma naught. So where we have replaced A2 by A naught. So you can, for different signals, you can calculate the probability of bit, where you know that A1 and A2 are represented by square root E magnitude, and so on. You can calculate the probability of bit error for different signals. So see, to minimize PB, that is the probability of error, we need to maximize this A1 minus A naught by sigma naught, or A1 minus A naught whole square by sigma naught whole square. So this is the in single power and this is in the double power. So we have A1 minus A naught square and sigma naught square, that is equal to ED. That is energy difference between the two. We represent by energy difference EG. Sigma naught square, that is the magnitude of noise variance. This is noise variance, and noise variance is n naught by 2. The value of noise variance is n naught by 2. So this will be 2 ed by a naught. Therefore, a1 minus a naught by 2 sigma naught will be equal to ed by square root in the square root ed by 2 a naught. So if you put here 1 over 2, keep outside a1 minus a naught square. So that is 2 ed by a naught. You can cancel this 2 by 2. This will be 2 square root 2 square root 2 square root 2. That will be 1 square root 2 will be cancelled. Another will be in the denominator. So that will be 3.73 equation. That is square root ed by 2a naught. So you can optimize this value that was in the equation. This one b.18. So you can replace this by 2 ed by 2a naught. Then the probability of bit error is given by equation 3.73. Then we have time cross correlation coefficient as a measure of similarity. That is equal to 1 over EB, that is energy per bit. Time period of symbol 0 to t, where this time cross correlation coefficient is in between -1 and 1, and is also equal to cos of theta. S1, S2 of t dt. So you either have this one or you can replace this by cos of theta. However, when S1t and S2t are viewed as signal vectors S1 and S2, then cross correlation coefficient is conveniently expressed by equation. Energy difference is equal to S1 square t plus S2 square t minus 1 S2 S1 and 2 S1t and 2 S2. And that is with the integration 0 to t. So energy bit will be equal to EB minus 2 psi EB. That is the last part of the equation. This one. Because we know that this cross correlation coefficient is equal to 1 over EB. But there is no EB, so you have to put EB by yourself and then replace 1 over EB 0 to t S1 of 2 by this factor, cross correlation factor, and EB will be there. So that will be 2 cross correlation and EB is equal to 2 EB1 minus this. So then substituting this equation 3.77 into equation 3, equation 3.73, we get equation 3.78. So this equation and this equation, they are same b.18, but in the different forms. This is in terms of A1 and A0, and this is in terms of energy difference between the two signals, and this is in terms of the energy per bit to noise ratio, and with respect to cross correlation coefficient, that is P, similar to P. So when we have binary signal vectors and antipodal signal, so the probability of bit error for antipodal signals like C. So when we have antipodal signals, so what will be the value of this one? Go back to C. So when we have two antipodal signals, that means there, what will be the angle between them? The two antipodal signals, दो antipodal signals के दरमियान angle क्या होगी? Like shown here. One is S1 and S2, so this is the angle between them. That is, how much angle is it? So the two antipodal signals have an angle difference of कितना difference है बेटा? What is the phase difference between antipodal signals? 280. Are you sure? Two eighty is too much. You can see what you can see from here. It is not 280. This one is how much is it? Yes, 180 is the correct one. 180 is the angle between the two. Yes, 180. So 180 cos of 180 is equal to cos of 180 is equal to -1. Very good. -1. It is -1. Now you see. So we will put -1 here. So that will be so we will put -1 here. So that will be 1 minus minus plus, and there will be 1 that will be 2 EB divided by A naught. And the square root. And that is same we have in equation. This one, probability of bit error for antipodal signals is 2 EB by A naught in the square root. Same, the probability of bit error for orthogonal signals is EB, because cos theta between antipodal signals will be EB1 minus cos theta, and cos theta will be between orthogonal signals, theta will be equal to 90 and cos theta is equal to 0. So 1 minus 0, that is 1. 1 will be multiplied with EB, so the equation will be Q function of EB A naught in the square root. Same you can calculate for the unipolar signals, that is EB by 2 A naught. So bipolar signals require a factor of 2 increase in energy compared to orthogonal signals, since 10 log of 2 is equal to 3 dB. So we say that the bipolar signals offers a 3 dB better performance than orthogonal signals. So as you can see in the figure, one are the orthogonal signals and one are the antipodal signals. So energy bit per noise ratio, that means is किसका बेहतर है 16 EBA naught or 13 EBA naught. More EBA naught means more energy per bit and less probability. So on the probability of bit error, antipodal is better, but on the power scale, by orthogonal is better, because bipolar signals require a factor of 2 increase in energy compared to orthogonal signals for the same power. So we need to choose the signals according to our whether we are power sensitive or whether we are error sensitive. If we need low bit error rate, a low probability of bit error, then we will choose the antipodal signals. If we need more power, but we are okay with the higher probability of bit error, then we will go with the orthogonal signals. For the same EBNR, that is 10 dB, the probability of bit error of orthogonal signals is 9.2 into 10 power minus 2. And probability of bit error of antipodal signals is 7.8 into 10 power minus 4. So which one is higher? Which one is higher probability of bit error? Orthogonal or antipodal? For the same receive signal to noise ratio, antipodal provides lower bit error rate than the orthogonal. As I already mentioned, that for the same power on the power scale, orthogonal is robust than the antipodal, but on the probability of bit error, antipodal has the lower bit error rate than the orthogonal one. Then we have relation between signal to noise ratio and EBNR. So this is how you can calculate energy bit to noise ratio from the signal and to noise ratio if you are given with the bandwidth and the bit rate. Then you can also read from the Bernard Sklar page 117 and 118. So in analog communication, the figure of merit used in the average signal power to the average noise power ratio, RSNR. In the previous few slides, we have used the term EB&R in the bit error calculation. How are the two related? EB can be written as S of TB, total signal, and the bit time of each signal, each total symbol and time period of one bit, and N naught is N over W. So we can replace S by STB, EB by STB, and N naught by N over W, and TB is equal 1 over RB, and W will be in the numerator. So that is SW by NRB. So thus EBNR can be thought of as normalized SNR. So SNR is the total value of signal to noise ratio, whereas if you want to calculate signal to noise ratio per bit, that is EBNR, then you have to take W and RB into account. Because is when we say SNR, that is a unitless quantity, but when we say EBNR, that is energy per bit. Means how much energy per bit and how much energy per how much noise per bit is there. So the two quantities can be related by this expression EB over N naught is equal to S over N W over RB. Then we have some example 3.2 that is solved here. Similar examples are there 3.4, 3.5, 3.6, and 3.7. So regarding mid, I already uploaded a file in the file section, which mostly include the some questions and problems. Please refer to that file. Your mid exam questions will be from those given there. If I add few more, I will share you then. But till today, I uh, just finalize those for your mid exams. Okay, if you have any questions, you can ask from this particular lecture. Now we have inter-symbol interference. That is the important, you can say, the impairment that needs to be reduced so that our signal can be propagate properly, can propagate properly. So one of the reasons that ISI can be with the signal, or your signal can have the ISI intersymbol interference in the detection process, is due to the filtering effects of the system. When we convert signal from analog to digital or digital to analog, we use filters. Due to that, ISI can be induced. So overall equivalent system transfer function is uh, transmitting transfer function, channel transfer function, and the receive function. So the total is the multiplication of these three: HT of F, HC of F, and HR of F. Creates echoes and hence time dispersion, causes inter-symbol interference at sampling time. So as the name suggests, inter-symbol interference means one symbol will be in the time of the another symbol. So that means one symbol is interfering with another symbol, and we call this inter-symbol interference, that interference between two symbols. And that ultimately will cause time dispersion and as well as problem with the sampling time. So that is Z of k. If Z of k is the received signal, then it is S of k plus N of k. That is transmitted signal noise and plus this inter-symbol interference or ISI induced noise or time dispersion. There will be the last factor. So the received signal can be given as in presence of ISI. So this is baseband system model, and we have the equivalent model where you can see we have symbols at the input represented as x1, x2, x3. These are the samples. Then we have transmission filter, uh, HT of F, and the output of this is the waveform, and that waveform is processed through channel. Channel induce some noise N of t, and the receive signal is supposed to be is equal to S of t plus N of t. And then we have receive filter, which will receive uh, after receive filter, we have the detector that will take one symbol at a time and will decide the based on some hypothesis whether it is S1 or S2, whether it is high or low. Equivalent model shown in the figure below, the base pair system model, where we can see the total transfer function equivalent system H of F that include HC of F, HT of F, and H of ARF. We have time dispersion. You can see the actual wave and the time delayed version of the same wave. Z of t is equal to Z dash of t is equal to N dash of t. So Z of k will be detected and X of k is received after detector. So again, it's a constraint of bandwidth. See, if we have the bandwidth, then uh, we can control the inter-symbol interference. How? Let's see. The theoretical minimum required system bandwidth to detect RS symbols per second without inter-symbol interference is RS by 2 Hertz. Whatever the symbol rate is, we divided by 2. That is the minimum bandwidth required theoretically to receive the symbols without inter-symbol interference. So symbols per second, like uh, if we use BPSK, then this symbols per second will be the same as the bits per second. So it's like 8,000 samples per second, or 8,000 samples will be transmitted as in the 256 quantization levels. Then that is one sample will be represented by 8 bits. So that will be 64 kilobits per second. So to transmit 64 kilobits per second, we need at least 32 kilohertz bandwidth so that the signal can be transmitted without inter-symbol interference. However, a system with bandwidth W is equal 1 over 2T, that is equal to RS by 2, because 1 over T is equal to RS by 2 hertz, can support a maximum transmission rate of RS symbols per second without inter-symbol interference. So that is Nyquist bandwidth, or the Nyquist formula, or the Nyquist theorem. Same is taken from the sampling theorem. So 1 over 2T is equal to RS over 2. So it's less than or equal to bandwidth, and then RS over W is greater than or equal to 2. That is symbols per second per hertz. So bandwidth efficiency, that is how many bits per second per hertz can be transmitted, an important measure in digital communications, representing data throughput per hertz of bandwidth, showing how efficiently the bandwidth resources are used by signaling techniques. So more number of bits can be transmitted per hertz, more efficient system is. So we have ideal Nyquist filter, and we have the ideal Nyquist pulse. So according to their bandwidth requirement, 1 over 2T. So Nyquist pulses filters which result in no ISI at the sampling time. And a Nyquist filter is its transfer function is in frequency domain is obtained by convolving a rectangular function with any real even symmetric frequency function. And Nyquist pulse shape is its shape can be represented by a sinc function multiplied by another time function. Examples of Nyquist filter are raised cosine filter. Pulse shaping to reduce inter-symbol interference. Now go back. Now you can understand why we have this figure. Now this figure where you can see we have a separate filter at the transmitter, separate filter at the channel, and separate filter at the receiver. So the three can be combined into one. And now this filter can be your Nyquist filter. And the Nyquist filter is your basically raised cosine filter that can be used as a pulse shaper to improve the inter-symbol interference or to reduce the inter-symbol interference. So because it is the shape that will induce the inter-symbol interference. If the two pulses are reshaped, then their shape is redefined, then we can mitigate or we can even eliminate the inter-symbol interference. So for that, we can use raised cosine filter. That is a type of Nyquist filter that is used to reduce the effect of inter-symbol interference. So what are the goals of pulse shaping filters? Its main goal is to reduce the ISI. And second one is to use the bandwidth efficiently. And robustness to timing occur, that is small side lobes. So time dispersion, basically this third one is the time dispersion that is due to the time dispersion. So it also improve or reduce the time dispersion. It also uh, increase the bandwidth utilization. It also reduce the intersymbol interference. So that is the transfer function of the race cosine filter. We also call that a Nyquist pulse, that is a rectangular pulse, and a sync function and a sync pulse in the time domain, and in the frequency domain it is the rectangular pulse. Excessive bandwidth W minus W naught, and this is roll off it. So that is in between 1. If it is near to 1, that means, or if it is 1, that means the numerator is higher than the denominator. That means we have the excess bandwidth. As the bandwidth reduces, roll off factor will also reduce. So the race cosine filter, as you can see in the baseband as well as in the passband, as R improves, so this is R is equal to 0. When we have perfect square pulse, and if we increase R, so that is R is equal to 0.5, and that R is equal to 1. At 0.5, and it is at it is 1, 0.5 and 1. Similarly, 0.5, 1 and 0, and R is equal to 1, R is equal to 0.5, and R is equal to 0. In baseband, it is equal to 1 plus R over RS by 2, because this is the bandwidth that we require, RS by 2. So, and the shape, when you use the any filter that will introduce this R factor, that is roll off factor. If it is R is equal to 0, then W will be equal to RS by 2. If it is R equal to 1, then bandwidth will be equal to symbol rate. Then we have pulse shaping and equalization to remove intersymbol interference. No ISI, no intersymbol interference at the sampling time. Square root raised cosine filter and equalizer. Taking care of ISI caused by transmission filter. Taking care of intersymbol interference caused by channel. So HE of is your equalizing filter, and HRC is equal to raised cosine filter, and HRRC is your square root raised cosine filter uh, that will take care of the uh, interference, intersymbol interference introduced at the transmitter and receiver filter. Whereas in the channel, it will be the equalizer that will take care of the ISI. This is the example of pulse shaping. So we have two pulses, blue and green one. So they are the actual pulses. So, and the black one is the reshaper that reshape the receive pulse using raised cosine filter into the black one, that can be uh, clear that we have the two consecutive data of 1 and 1, and then we have the -1. If we transmit this without pulse shaping, then you can see they are interfering with each other. They means they have the intersymbol interference, and without reshaping or the pulse shaping, the receiver or the detector wouldn't understand the two pulses because they are into each other. They are into each other's time. But now they are separate, and the detector can understand them easily. So this is the baseband receive waveform at the mesh filter output that will have 0 intersymbol interference. Then we have an example that says find the minimum required bandwidth for the baseband transmission of a 4-level PAM pulse sequence having a data rate of this. If the system transfer characteristic consists of a raised cosine spectrum with 100% excess bandwidth, and B is also something that they ask. Solutions are there. We have calculated A, and then we have B. Similar examples are given 3.4, and same unsolved examples are given in the from the Nyquist, from the Barnard scale. They are also listed here. And we have this 3.12. Okay, so that is the end from the intersymbol interference. If you have any questions from intersymbol interference, you can ask. So this is our next lecture that we'll do tomorrow, inshallah. So your mid will include all the lectures till today. Okay, that we our last topic was the intersymbol interference. That will also be included in the mid exams. Your DP paper will be on, I think it is on 6th June. 6th, and on 6th June we have one paper, and 7th June we have the other. Let me see. So digital communication is on Wednesday, that is 7th June. 7th June, yes, it is on 7th June. So I already shared you with the few tentative questions, but I will finalize this list on uh, maybe on Saturday or maybe on Sunday. Yes, on 27th or 28th. Okay, so then you can go for the preparation. Then you still have enough time for the preparation, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 days. Okay, same for the wireless communication. Most of you also enrolled in wireless communication. So that paper is on 6th, that is on Tuesday. For that, I will also share the tentative questions on uh, up to 28th of the May. Okay, so both subjects, digital communication and wireless communication, uh, whatever you say, the help from my side will be shared up to till 28th. of May. Still you have, then you have 9-10 days for the preparation. Okay. Okay, thank you. Have a nice day. If you have any question up to now, you can ask. Else we stop here.